Hi everyone! In this video, we continue our study on the Euclidean algorithm. Previously, we have shown what is a Euclidean algorithm, how it works, and why it works. In this section, we're going to look at the speed of decay for the sequence of remainders achieved from the Euclidean algorithm. We already know this sequence must go to 0. But will it go to 0 in a very fast speed or in a very slow speed? And that will be the topic of our investigation today. More precisely speaking, we would like to show that the remainder is at least halved after every 2 steps. How do we prove this? Well, we will discuss 2 cases based on the value of rk plus 1, which is the intermediate term between rk plus 2 and rk. In the first case, let us assume that rk plus 1 is already less than or equal to 1 over 2 times rk. If that is the case, we know that rk plus 2 is less than rk plus 1 strictly. Thus, it is also less than 1 over 2 times rk, and the statement is proved in this case. Otherwise, rk plus 1 is greater than half of rk. If that is the case, let us recall the equality in the Euclidean algorithm that links these 3 terms, rk, rk plus 1, and rk plus 2. From there, we can try to compute rk plus 2 and express rk plus 2 using rk and rk plus 1. That gives rk plus 2 is equal to rk minus rk plus 1 times qk plus 2. But since our sequence of remainders is keep decaying, we know that all these quotients q must be a positive integer, which means it is at least 1. Hence, rk minus rk plus 1 times qk plus 2 is less than or equal to rk minus rk plus 1. And now, using assumption that rk plus 1 is greater than half of rk, we see that the term is less than rk minus 1 over 2 rk, which is again 1 over 2 rk. So in the second case, we have also proved this statement, and this finished the proof for the whole proposition. Alright, now before this proposition, we know that the sequence of remainders is decreasing, but that's all what we know. So if we compare rk plus 2 and rk, we know that rk plus 2 in the worst case might be rk minus 2, because in the worst case, each step the remainder might only decay by 1. Hence, rk plus 2 under that estimate can be as large as rk minus 2. And this only permits us to conclude a linear decay for the sequence of remainders. However, with the consequence of the above proposition that we have just proved, we know that every 2 steps, the remainder is halved. And this tells you the decay is actually exponential. Hence, the algorithm will not only terminate in finitely many steps, it will in general terminate very fast. Of course, it is not our ambition here to develop a detailed investigation for the optimal speed of decay under various settings for the Euclidean algorithm. We merely want to point out rather that decay is at least exponential, which is already a very desirable fact in practical applications like cryptography. This finishes our discussion on the Euclidean algorithm. In the next section, we will turn to the Bezout identity.